the last part of fluid mechanics for interview preparation. So, in fluid mechanics, the important law to be discussed is the Newton's second law. So, as we know that the external force is nothing but the change in momentum, that is dp by dt. And if we exaggerate the formula of momentum, so it is mass times the velocity. So we know that dmv by dt. So when we transfer this dt to the other side, that is force times the change in time, is basically called the impulse. Impulse is nothing but force times the change in time is equal to dmv, change in momentum. So when we divide the dt on the both side, we get such an expression in which force is equal to mass flow rate times the change in velocity. So this is what we are going to use in the next section, which is basically jet propulsion. So jet propulsion, or we are discussing about the impact of jet. So impact of jet on a fixed plate. So what is the force applied by the water jet on the plate? So to know the force, all we have to do is to know that the velocity of the jet from the nozzle, let's say, is considered as Vx1 is equal to V, and its plate is fixed. That means the velocity is zero here. U is zero. So the force basically is equal to the change in momentum, and that is mass flow rate times the change in velocity. And the change in velocity is nothing but Vx1 minus Vx2. Vx2 this here, and that is Vx2 is zero. That is why mass flow rate times velocity is the formula. And when we as we know that mass flow rate is nothing but q times v sorry density times q is a discharge, q is equal to area times velocity. So density times area times velocity times v, that is rho a v square, that is the force applied on this plate, okay, due to the jet. And when the plate is moving, let's say this plate is nothing but the blade of a particular turbine, and this is shaft here, and this is radially mounted plate basically. So when jet is applied here, and this jet basically moves the blade, and this blade already has a velocity of u. So what is the force of this blade here now? So as we know that force is mass flow rate times dv. dv is nothing but the change in velocity of here to here. And as we know that the change in the first velocity Vx1 here is nothing but is basically the relative velocity of the jet as well as the plate. So jet is moving at velocity v and blade is moving at velocity u. So the relative velocity will be v minus u. If the velocity, let's say, it is greater than the jet velocity, then maybe the jet even won't touch the plate. So that is not the case basically. So in that in the actual situation, the velocity is less than the jet, the velocity of the blade is less than the jet, so that is why the relative velocity will be v minus u. And in this case, we always consider that for this case, uh, some reference we have to consider. So we make this blade as a reference. That means the velocity will be zero here. We consider that velocity is zero. In that case, when we say mass flow rate times change in velocity will be vx1 minus vx2, and that will be, as vx2 is zero, the vx1 will be v minus u, and total force will be rho av times v minus u, okay. And there's a general formula for blade velocity, which will be u is equal to pi dn. N is the speed, rotation speed, that is rpm, divided by 60. This is the blade velocity, total blade velocity, okay. And the blade power or runner power, which can be expressed as force times the blade velocity, okay. And the fluid power will be basically kinetic energy, uh, similar to kinetic energy, but it is half m mass flow rate times v square. So this is the fluid power. And the hydraulic efficiency, to see how much efficient the turbine is, to the formula for the hydraulic efficiency is blade or runner power by fluid power, and which is expressed from the above formula. It will be something like this. So what blade velocity should be for the maximum hydraulic efficiency? What should be the u for the maximum hydraulic efficiency? For that condition, the maximum for maximum hydraulic efficiency, the differentiation of hydraulic efficiency with respect to the changing velocity should be zero. Changing blade velocity should be zero for the maximum hydraulic efficiency. In that case, we see that the velocity, the blade velocity should be half of the jet velocity. Okay, and as we know that blade velocity formula is pi d n by 60. So as we know the u, from that we can get the rotation speed. So we can set that kind of turbines which has this rpm. So if you use that turbine, we will get the maximum hydraulic efficiency. Okay, so this is the blade for a turbine. Let's say this is a shaft here and this is the blade here. So in this case we can see that the fluid will enter here. This is V1 is basically absolute velocity of the fluid entering through the jet, and this 2 is the exit point where the fluid goes outside, and this entering point is called the inlet angle, and the exiting point is called the outlet angle. And the diameter which we in the coming case will use is d as this point, the exit points, and the d1 will be the inlet points. Okay, so let's discuss about the velocity diagram. So just forgot to mention these points here. So Newton's law. From Newton's law, how to find the impulse, as we know, F times dt. And from this, how to find the external force via mass flow rate and change in velocity. We have discussed that. So impact of jets. This is the picture. As we discussed, this one. What is the force applied on the jet on the plate, and what about the work and the power? So for in this case, as there is no work done, there is no change in velocity of the plate, so work will be zero as well as the power will be zero. Okay, so that's the picture shown here. And for the moving plate, so what is the force applied on the jet on the plate? We have discussed relative velocities. So these are the relative velocities, v minus u. It's explained. So the blade velocity formula is explained with respect to the RPM. What's the blade power, fluid power, hydraulic efficiency is discussed. How to get maximum hydraulic efficiency, what should be the blade velocity, they are discussed already. Okay, so this is the basic formula as we have already discussed the hydraulic efficiency. We will see about the overall efficiency. Overall efficiency is nothing but the hydraulic efficiency times the mechanical efficiency, which is basically shaft power divided by the fluid power. We will see that. So about the velocity diagram. So let's discuss about the velocity diagram. So this similar diagram is explained here. So we'll see what we have to discuss is the nozzle angle, inlet, outlet, bleed angle, direction of relative velocities, components of absolute velocity, fluid flow velocity, bleed rotation velocity, formula for hydraulic efficiency, net head. We'll see that. So this is the blade. Let's consider this as a blade, and the jet is here. This is the point. The jet enters here. This is V1. This is absolute velocity. The jet enters here, and when the jet enters here, what happens is that this is the attack angle. After entering here, the velocity of the direction of the fluid flow will be along this radial line. This radial line is nothing but tangent of this entering, tangent of this plate. Okay, so when we throw the water here, at this when we throw this at this angle only, then the flow will pass along the blade uniformly, properly at this direction. So this is basically the nozzle angle alpha, and theta. Theta is the inlet blade angle, and phi is the exit blade angle. This is the phi exit blade angle. Okay. So as we know that this is the blade velocity here, the overall blade velocity. For when entering, when the fluid is entering, at that point the blade velocity will be u1, and this same velocity vector is transferred here, and a triangle is made, and this is nothing but the absolute velocity is nothing but the blade velocity at the inlet plus the radial velocity. Okay, and for turbine, always the absolute inlet absolute velocity will be greater than outlet absolute velocity. If it is less than the outlet absolute velocity, that means it's a compressor. Okay, and as we know that u1 u2 are nothing but the blade velocity, and this is general formula for that. And I have discussed that d1 d2 is nothing but the diameter. This is the diameter from the inlet and the diameter of the outlet. Okay. And this is the formula for hydraulic. Okay, first we will discuss what are the relative velocity. As we know, this is the relative velocities. and V1, V2 are the absolute velocity. For the absolute velocity, there are basically two components. One is the fluid flow velocity component, and another one is the whirl, whirl flow velocity component. So what is this means? This velocity flow makes sure that the fluid will flow throughout the blade, and this whirl velocity makes sure that this blade rotates. This is the velocity component which makes the blade rotate along the shaft, and this one makes sure that the fluid flows throughout the blade and exits here. Okay, so the two components are divided like that, and you will see that for in this case where the fluid is going through this tangentially with respect to the shaft. In that case, the net head available will be gross head minus the head loss. We will discuss this later. And the hydraulic efficiency nothing but the as we discussed earlier, hydraulic efficiency will be the plate power by the fluid power, and we have to use this same formula here. If you use the same formula, we will get a similar equation. Okay. So next, we will discuss about the hydraulic power, and we have discussed all these points. Okay. So we will discuss about the hydraulic power plant. So what are there any pollutions happening due to hydraulic power plants? Any three biological reasons, one geological reasons. What are the uses of hydraulic power plants? So yes, hydraulic power plants creates pollutions. The first reason is the water salinity. Water salinity increases inside the in the cultured water dam. Vegetation loses because of the large construction. Vegetation loses as well as the vegetation due to higher salinity. The bio marine life also gets affected. Vegetation inside the water also is affected, and it also pollutes the soil. Soil pollution happens. And there is a geological point is that due to the pressure on the land, some big earthquake-like situation can happen. Okay, for example, in the China, you can see that it's a big dam. If the dam breaks out, it was said that due to that, rotation of the earth can change. So because of the faulted mass or the pressure on the particular land, and there are many uses. Important uses are basically it can be used for irrigations. In past, they were mainly used for irrigation, and now it is also used for the power generation purpose. So let's discuss about the two important kind of turbines which are basically used in the dams in the hydraulic power plants. First one is the impulse turbine, which is something like this. Impulse turbines, and what are the points to observe in that? So what is the net head? As we have discussed earlier, what is the net head? How to measure the gross head? What are head and the tail race? What is the velocity formula of the jet from the nozzle? How does the kinetic energy, pressure energy applicable in this impulse turbine? Why it's called impulse turbine? Does it operate under high pressure? You will see that. You will see in divided parts. Okay. So case one for impulse turbine. So one of the example of impulse turbine is Brayton turbine. It is something like this, where the water flow tangentially. So what happens is that this is a dam, imagine, and this is called the head race. The top point of water is called head race, and the lowest point of the water release is called tail race. So what happens is that when the water is stored and released through the penstock, through the nozzle, and it goes out to the nozzle hits the impinges the water on the turbines to generate the power. So what happens in this process is that there is a net head loss, and the net head loss is calculated as the gross head. Hg is the gross head, and gross is nothing but the distance between the head race to the exit point of the nozzle. So this is the exit point. So the gross head will be here to here. Okay, for the impulse turbine, and this is one of the head, and this is another head loss will be that is due to the penstock. There is a friction in the penstock, so due to that the velocity is decreased, and that is the hedge off is nothing but the head loss. As we know, the total energy is here. There's a pressure energy uh, of the water. So when we release the water from here to here, when it reaches out, there is total the energy gradient line will decrease from here to here, due to the head loss, mainly to the head loss in the penstock. So the total net head will be H is equal to Hg, as we discussed, minus Hf. Okay. So H is used to find the energy of the fluid at the exit. You will see that. And as we know from the previous formula, from the Darcy equation, the head loss formula is this. And the velocity at the exit from the nozzle of the water is basically V is equal to CV root G to GH. H is the net head. And CV is nothing but the coefficient of velocity we discussed earlier. So in impulse turbines, the jet is impinged on the blade to generate the power, and one of the examples is the Pelton turbine. So we will discuss about what happens into the all these 3 points later in the section. We will now go to the reaction turbine. Some of the examples of the reaction turbines are Francis, Kaplan, and Polar turbines. Okay, so this is the reaction turbine. So we will discuss it. What about the kinetic energy, pressure energy happens inside this Pelton turbine? Uses of draft tubes, we will see that. And does it operate under high pressure or closed chamber? Why reaction? Why it is called reaction? Direct difference in pressure in flow in reaction to it generates force. We will see that. We'll discuss it. Where are free and forced products applied? Purpose of guiding plates. In which part of the pressure energy is converted to the kinetic energy? Where does the cavitation occurs in the turbine or compressor? So basically, this is basically the reaction turbine, as you can see here. And in this case, in the previous case for the impulse turbine, only the kinetic energy is applicable, as the all the pressure energy inside the fluid is basically converted to kinetic energy, and that is what creates the velocity here, v of the fluid, and that hits the blades of the turbine. And in this case, because of that, as all the energy is converted to kinetic energy, and that in turn developed as the momentum. In this case, the velocity will be very high compared to the reaction turbine. But in reaction turbine, there are both the things: kinetic energy, pressure energy. And there are some examples like Francis turbine, Kaplan turbine, and the impeller. What happens is that this is the dam, this is the head race here, and the gross head for the reaction turbine will be calculated from the head race till the tail race, because this is where the water is released completely. This is how it's calculated. And what happens is the water flows here and goes inside the chamber, closed chamber, and it rotates the turbine, and water is released through the draft tube. Because the draft tube connects to the uh, water level here, tail race. What happens is that when it happens, it maintains the main head, so it doesn't change. The head doesn't change. And there are another uses of the draft head. We will see that later. So classification of hydraulic turbines. So the hydraulic turbines can be classified in certain cases. For example, in on basis of energy available in the inlet. So energy available in the inlet are divided in two ways: impulse turbine and reaction turbine. So in impulse, we know that another example is Pelton turbine, in which this turbine operates in atmospheric pressure conditions. As we know that from this picture, you can see that the water is released uh, directly on the turbine from through the turbine. So what happens is that when the water is coming outside, it's already in the atmospheric pressure. While the reaction turbine, there is a very high pressure, and when it goes to the when it goes inside the turbine, the pressure is already reduced. You will see the reasons later. So uh, in this case, in this impulse turbine, the RPM is very high, the velocity of the turbines are very high, but the power is comparatively generated is low. So the impulse is basically F times dt is equal to change in momentum dp. So it is called impulse because the only source of energy in the fluid is the kinetic energy, and that creates force on the blade due to change in momentum. So that is why all the energy of is basically kinetic energy. All the energy is converted to kinetic energy, and that kinetic energy of the fluid is uh, converted as a change in momentum, and that momentum creates force. Or that change in momentum creates impulse. That impulse um, is what moves the blades. That is what is called impulse turbines. While in reaction turbines, the RPM relatively the RPM is less, but the power is very high because both the kinetic energy and pressure energy are used in the inlet. This, these are basically operated in very high pressure because both the things are there. Pressure energy as well as kinetic energy of the fluid is there. So in this case, the turbines work under high pressures in closed chambers. And the difference of pressure, what happens is that the change in pressure on the path, the change in pressure, that creates a reaction force, and that reaction force is what generates the power. So that's the key word of the reaction. The change in pressure creates a reaction force. So this is a green picture of the reaction turbine. You can see that separate impulse turbine here. So the kinetic energy is what creates the momentum, and that momentum in return develops the impulse. That's what moves the Pelton turbine. And while you can see in reaction turbine, outside the turbine, outside the blades, you can see this is basically a free vortex. That means in from the center, the it is not in, it means the torque is not induced here. And when we go to the here, it is a free vortex. There is no induced torque. When we go to the center here, it is a forced vortex. The torque is basically induced. That's why because of the guiding blades, you can see that these guiding blades allows the uh, fluid inside guides the fluids inside the runner. So what happens is that already the pressure is high here, and when this fluid is entering inside the small area, as the area is entering, when the area reduces, the pressure also reduces. And at this point, as from the Bernoulli equation, we have seen that when this happens, the velocity also increases. When pressure decreases, velocity increases. Okay, and in this place, in this guiding blade area, only the pressure energy is converted to the kinetic energy. And when water is released, what happens is that the due to the reduced pressure of the fluid, the pressure may be less than the atmospheric pressure. So we cannot release the water in vaporized form. So what we have to do is to bring back the fluid's pressure to the atmospheric pressure. So that's why we use the draft tube, so that the fluid won't just evaporize. So these draft tubes, the fluid is exit thrown outside through the draft tube, and this basically condenses and it mixes with the other water. So it brings back the fluid back to the atmospheric pressure, and at the exit point, the pressure can be less than the atmospheric pressure, and it is basically also used to maintain the head, okay, as we discussed earlier. So what happens, as we know that there is a cavitation problem whenever there is, as we've seen in the nozzle case, when there is sudden increase in the area, the pressure increases, and due to that low pressure to high pressure, is a sudden increase of the pressure of the fluid. What happens is due to the sudden increase in the pressure, uh, when the fluid pressure is less than the atmospheric pressure, uh, less than the vapor pressure, less than the atmospheric pressure, the water starts boiling. Due to that bubbles, there's a pitting effect on the surface of the body, and due to that cavitation happens. So cavitation in this case can happen at the exit of the runner and the entry of the draft tube, and in compressor it can happen in the entry of the impeller. Okay, and next is uh, this is classification. As I said, again the classification can be based on the direction of fluid. So uh, let's see. What about the RPM and the power? We'll see that. So on basis of direction of flow, so if the direction of flow is axial to the turbine, this is shaft, and along the shaft if the water flows, and this is called axial flow turbines, and some of the examples of the Kaplan and impeller. So you can see Kaplan and impeller, and both are basically reaction turbines. And if the flow is radial along directly like this, Then it is a radial flow turbine, and one of the example is Francis turbine. Okay, and if the flow is tangential, like this, in the Pelton turbine, is one of the examples of Pelton turbine. And if there is a mixed flow, if it is radial as well as axial, it goes and comes like this. It is called mixed flow, and in this are this happens in modern Francis turbine. Okay, so and next is what can we say about the uh, discharge as well as the head of particular turbine. So as we know that the power is nothing but the density times discharge times gravity times the specific head. So usually for a Pelton turbine the discharge is less. We have discussed this earlier so in the fluid dynamics. So for the Pelton turbines the discharge is less but the head is high. They are used at that point. For Kaplan they are used when the discharge is high and head is less. And Francis turbines are basically used when these are basically moderate values. So one of the way to choose the turbines uh, for a particular situation, let's say we have a certain head in the given situation, like in my the head is high, and we know that discharge is limited some amount like that, and to get some high efficiency, we have already chosen the RPM, the speed on the blades rotation speed RPM, and we want to choose the turbine, which kind of turbine we have to choose. For that, we need the um, specific speed. The specific speed formula is this: n times root of the power divided by the head of power of 5 by 4. Okay, so if you know the value of the RPM, if you know RPM, the power, and the head, so using this values, we can decide the turbine using the specific speed. If the specific speed value is something, we have some specific fluid value, specific speed value, then with that value we can match this value with this range and we can use it turbines. So if the NS is in this range, we have to use the Pelton. If this range, then we use Francis. For Quebec it is 300 to 1000. So under so we can basically use uh, turbines with we can select the turbines using the specific speed value. Okay. So next is the discussion about the Pelton wheel with respect to the efficiency. So let's say the Pelton wheel is here. As we know, the Pelton wheel, I will show you the picture. So this is the Pelton turbine and this is the Pelton blades. It is something like a bucket shape in which there is a intersection, something like this. Okay. So Pelton turbine is also impulse turbine category. The flow is tangential. In this case, the RPM is less, discharge is less, and used in where the head is high. So these are hemispherical blades. Okay, the water enters here like this. So this is entry point 1 and this is exit point 2, and we know the velocity of the jet is CV times root of 2gh, and net head is hg minus h of a discussed earlier, and the d1 d2 are here for the blade velocity. Okay. So for this, how do we know the efficiency? We'll discuss that. So this is the velocity diagram for the Pelton wheel. So what the points we have discussed: the nozzle angle, inlet outlet angle, direction of relative velocity, components of the observed velocity. We'll see. We have discussed it earlier, and we will know it here also. Relative velocity, impulse turbine. What is the relative velocity condition? Absolute velocity is how do we know it's a turbine or compressor? We had discussed earlier. The formula of hydraulic efficiency, mechanical efficiency, and overall efficiency. We'll see that. So this is the velocity diagram. So in this case, the nozzle angle as well as the inlet angle will be 0 because it is horizontal to this point here like this. This is the object V1 is the object velocity. U1 is the uh, U1 will be the blade angle and VR1 is the relative velocity, and VW1 is the whole velocity. Okay, and there is no uh, flow velocity. If Vf1 because given this angle. So water enters here and releases outside like this. So this is absolute velocity V2, relative velocity, and flow velocity, wall velocity, and the blade velocity. So this is the exit outlet angle, not outlet blade angle. So we have discussed, and for Pelton turbine, Pelton wheel, this angle, uh, if we the exit well, the V2 uh, VR2 relative velocity V2, the angle will be this 165 degree. Okay. So as we know that V1 absolute velocity is equal to VR1 plus U1. What happens is that for impulse turbine, the relative velocity of the outlet should be less than the relative velocity of the inlet. Okay, this is the condition for the impulse turbine, and as it is less because of the coefficient of friction. So VR2 is equal to K times VR1, and K is basically coefficient of friction. So if the absolute velocity of inlet is greater than outlet, it is turbine. If the absolute outlet velocity is greater than absolute inlet velocity, it is compressor. Okay. So the hydraulic efficiency is nothing but the runner power or the fluid power divided by the fluid power. So the formula is this, and the efficiency of the machine is nothing but the shaft power divided by the runner power or blade power. The formula is something like this. So from the velocity diagram, the world velocity will be VR1 cos phi minus U2. So this world velocity VW2 will be VR2 cos phi minus U2. Okay, so it is understood. And as we know that the VR1, the formula is here, the VR1 will be V1 minus U1. V1 minus U1 or V2. Okay. So when we put this value here and put it here, so we know we have some value for the world velocity 2, and VR1 is nothing but V1 minus U. And when we put this value inside this formula, so we get the hydraulic efficiency something like this. And we know from this formula that the hydraulic efficiency is a function of the bleed velocity. So for high efficiency, the condition is the change in efficiency with respect to the change in velocity should be zero. And from that we know that the bleed velocity should be half of the inlet absolute velocity. In that case, we get the hydraulic efficiency as 1 plus cos phi by 2. Okay. And the whole efficiency is nothing but the hydraulic efficiency times the mechanical efficiency, which is basically shaft power divided by the flow power. And we had discussed earlier that the if V1 is greater than V2, it is turbine. V2 greater than V1, it is compressor. If the relative velocity VR2 is less than VR1, it is turbine. It is impulse turbine. If VR2 is greater than VR1, it is reaction turbine. And let's discuss about the Francis turbine. So Francis turbine is a turbine in which the fluid flow is radial, and it's a reaction turbine too. And the same thing I had to discuss what the efficiency, hydraulic efficiency of this in this case. So again, so this will be the absolute velocity, and this is the nozzle angle. This is the inlet blade angle. This is the outlet blade angle. Well, the difference in this thing is that there is no uh, world velocity. As you can see, the world velocity is zero here, and we only have the uh, absolute velocity, absolute exit velocity, which is equal to the fluid flow velocity Vf2. So V2 is also is equal to Vf2, but Vw2, the world velocity exit, is zero. So in this case, as we know, the relative velocity of the outlet should be greater than the inlet relative velocity. Okay, so the VR2 should be greater than VR1 for the because it is a reaction turbine. So we know that Vw2 is zero, and in this case, the Vf1, the fluid flow velocity of inlet and outlet will be same, and in this case, the hydraulic efficiency formula is this, and the final hydraulic formula for reaction turbine is this. So what we have to notice is that in reaction turbine, the outlet fluid velocity is zero, and the fluid flow velocity of inlet and outlet is same. Okay. So this is the difference here. So last point to discuss is the degree of reaction. So what is the ratio between what is the total energy, why kinetic energy is not considered? So degree of reaction is basically the ratio of pressure energy change in the blade or runner by the total energy change. So if you want to know the effect of pressure energy with respect to the total energy, what happens is that in reaction turbine, the kinetic energy, the pressure energy, sorry, the kinetic energy, sorry, the pressure energy is converted to the kinetic energy. But what portion of kinetic energy is part of the total energy? What amount of pressure energy acts on the total energy? We want to know that. For that reason, we use R. Okay, and as we know, the runner power is basically mass flow rate times the velocity. This one, and the total runner power is nothing but the total energy, and it's nothing but the kinetic energy plus the pressure energy. Okay, so that's it. Thank you.